Imagine a material strong enough for the tallest buildings or longest bridges, yet versatile enough to take on any shape or form. It would never rust or rot, never need painting, and would resist fire. It's concrete, the most widely used building material on Earth, one with the natural properties of the stone from which it originates, plus its own unique qualities. The secret to this remarkable material is one essential ingredient, the glue that binds stone and sand together into concrete, the fine gray powder called Portland cement. Portland cement is a man-made substance born of some of the Earth's most abundant elements: limestone, clay, and sand. Their transformation into a new material was invented by Joseph Aspdin, an English stonemason, in 1824. He called his cement Portland because concrete made from it resembled a prized natural building stone found on the Isle of Portland, off the British coast. So Portland cement is not a brand, but the generic term for the type of cement used in virtually all construction. When Aspdin mixed his new cement with sand, water, and crushed stone, a remarkable change took place. Water and cement blend into a paste that coats the surfaces of the stones and sand. Through a chemical reaction called hydration, cement gel and crystals form to fill the spaces occupied by the water, binding together the sand and stones. And here lies the key to concrete's dexterity. It's pliable when freshly mixed, strong and durable when hardened. Properties that make concrete unnatural for architects and engineers.
It's a fun material to use for an architect because it makes one more of a sculptor than an engineer in a certain way. Because it has, I mean, some of the most unique structures that have been designed in concrete. It's fabulous as a sculptural, expressionistic material, more than other materials because of its fluidity.
The basic versatility of concrete is the ability to be molded to any shape and size that you want. That gives you an artistic license to deal with it as a design material and gives you a great deal of freedom.
Concrete begins with cement, and cement begins at the quarry, where explosives break rock from the face.
Fire in the hole!
These slabs of rock are crushed to the size of baseballs, then further reduced to gravel. While the plant's quarry yields the principal ingredient, limestone, other raw materials are often brought in from outside sources. All materials are carefully analyzed to determine the exact proportions of chemical compounds needed for the cement. After the materials are automatically proportioned, they are ground to a fine powder in massive rotating mills, then blended, homogenized, and tested again. In an alternate method, known as the wet process, water is added during grinding to produce a creamy mixture called slurry that is blended and stored in tanks. Whether as slurry or dry powder, the ground raw materials, called raw meal, are ready for the kiln, a huge rotating cylindrical furnace. At the heart of cement manufacturing, the kiln is the world's largest moving piece of industrial equipment, and one of the hottest. Here's how the process works. Some cement plants save energy by preheating the materials just before they enter the kiln. The raw meal swirls down a series of cyclone chambers, where it is heated by hot exit gases from the kiln. From the preheater, the raw meal enters the kiln at the upper end. As the slightly inclined kiln turns, the materials move through progressively hotter zones. At the lower end, a burner, fueled by powdered coal, coke, or natural gas, feeds a flame that reaches 3,400 degrees Fahrenheit. Some producers supplement fossil fuels with high-energy wastes, such as scrap tires, motor oil, solvents, or paints. This practice not only saves energy, but safely disposes of these wastes. Chemically, these wastes are similar to the fossil fuels they replace, but often burn cleaner than coal. As the raw materials slide and tumble down the rotating kiln, they're gradually heated to 2,700 degrees Fahrenheit, becoming partially molten. Under this intense heat, individual molecules break apart, then recombine to form a new compound called clinker. When the marble-sized white-hot clinker emerges from the kiln, it's cooled and hot air is returned to the kiln to save energy. Throughout the process, all materials are constantly sampled and tested for high and consistent quality. Cement must meet the stringent standards set by the American Society for Testing and Materials. Such vigilance extends to emission controls. All processes are carefully monitored and regulated from the central control room. Precise computerized controls enable cement plants to meet the highest air quality standards. Once the clinker is cooled, it's mixed with a small amount of gypsum, then ground into the superfine powder called Portland cement. Finished cement is pumped to giant silos for storage. From here, it can be bagged for customers who need only small quantities, but most Portland cement is sold in bulk shipments. From a central control room, operators ensure safe and efficient loading of cement into trucks or rail cars. From the plant, most cement goes to ready-mix concrete producers. Here, the cement is mixed with sand, gravel, and water to create concrete, which is delivered to construction sites in the familiar trucks with revolving drums. Cement is also used in concrete block, an array of precast concrete products, and to make mortar for brick and block. Ultimately, it forms our roadways, patios, buildings, skyscrapers, and more. And not only is it the most versatile of building materials, concrete is also among the most energy efficient. Its production requires only a fraction of the energy required to produce steel, brick, plastics, or aluminum.
You can look at various materials in terms of the total energy content of the material. From the time it is excavated from the ground, from the materials, basic materials, and from the time it's produced, all the labor it's taken to fabricate the material and put it up, what is the energy content of a material? One finds that since concrete uses natural materials from the ground, it has considerably less energy content compared to other materials.
Once in place, concrete's mass resists temperature swings, reducing the heating and cooling requirements for homes and buildings.
Concrete is a very environmentally believable material with respect to reduction of energy usage of fossil fuel and other energy sources because of its mass and its terrific resistance to thermal interchange because of its mass, because of its density. So that in that sense, environmentally, it's a very good material. It's a dissimulative material. You can play with it. It can become what you wish it to be. That's where it's interesting. I mean, it's interesting also environmentally because of the lack of fossil fuel and all of that. But I think at another level, it's a lot of fun.
From quarry to kiln to construction site, concrete is the cornerstone of all that we build, a manufactured stone rivaling its natural counterpart in strength and durability, yet far surpassing it in uses and versatility. Our modern high-tech Stone Age begins with a fine gray powder called Portland cement.
This videotape has been designed to introduce you to the fundamentals of quality concrete. Quality in this case means concrete that has been designed and constructed to meet the conditions under which it must serve, whether in a pavement that endures freezing and thawing temperatures and the corrosive effects of de-icing chemicals, the foundation of a high-rise building supporting the weight of 50 or more stories, or the attractive patterns in a decorative concrete. Let us begin by examining the basic constituents of concrete. Wherever or however it is used, concrete is essentially a mixture of two parts, paste and aggregates. The paste is formed from the mixing of Portland cement, a manufactured product made to exacting standards throughout the world, and clean water. When the aggregates are added, sand and gravel or crushed stone, they become evenly distributed throughout the mixture and completely coated with the paste. The paste completely fills all of the spaces between the aggregate particles. The mixture is bound into a rock-like mass as the paste hardens because of the chemical reaction between the cement and water. For concrete mixes, there are two classes of aggregates, fine and coarse. Fine aggregates consist of natural or manufactured sand, with particle sizes ranging from dust up to about 1/4 inch. Coarse aggregates range from about 1/16 inch to whatever size can be accommodated by the particular construction. Since aggregates make up about 3/4 of the concrete volume, they must be selected with care. Most specifications stipulate that they should meet the requirements of ASTM C33 standard specification for concrete aggregate. The quality of the in-place concrete depends on a number of factors, but primarily it depends upon the quality of the paste. The paste largely determines the strength, durability, water tightness, and abrasion resistance of concrete. The relative amounts of water to cement in the paste is called the water-cement ratio. It is expressed in terms of pounds of water to pounds of cement. A correct relationship is essential to quality concrete. The ratio of water to cement must be carefully controlled to produce a mixture that will develop sufficient strength and water tightness. Generally, the less water used, the better the quality of the concrete, provided it can be adequately consolidated, as this typical trial mix strength curve shows. Let's illustrate the importance of the proper water-cement ratio by compression testing two concrete cylinders. The first cylinder was made from a concrete mixture with a high ratio of water to cement, 7/10 of a pound of water to each pound of cement. The second cylinder was made from a concrete mixture with a low ratio of water to cement, 4/10 of a pound of water to each pound of cement. The cylinder made with the high water cement ratio tested at 2,050 pounds per square inch. The cylinder made with the low water cement ratio tested at 5,450 pounds per square inch. Proof that concrete strength varies with the amount of water used with a given amount of cement. The water-cement ratio affects all of the desirable properties of concrete, such as durability. These laboratory specimens, for example, are undergoing daily cycles of freezing and thawing to test their durability. This simulates the most destructive weather conditions that concrete can face. These test specimens from left to right were made with decreasing quantities of water per pound of cement. Those with less water show less damage after 200 freeze-thaw cycles. Additional durability is provided to concrete by adding air to the mixture through an air entraining agent. This can either be ground into the cement during manufacture or added as an air entraining agent to the water during mixing of the concrete. The admixture creates billions of tiny air bubbles that are dispersed uniformly throughout the paste. These provide minute pockets where excess water can expand during freezes, relieving pressure on the concrete. These laboratory specimens show how entrained air dramatically improves concrete's resistance to damage from cycles of freezing and thawing. The specimens were subjected to 150 freeze-thaw cycles in the laboratory. The specimen with adequate air entrainment showed very little damage. By contrast, the specimens with insufficient air entrainment or without entrained air showed increasing damage from the destructive effects of the freeze-thaw cycles. Other admixtures or ingredients are sometimes added to the concrete mix to offset unusual working conditions or create special properties. During hot weather, a retarder can be added to the mix to slow down the rapid setting time of the concrete, which makes placing and finishing difficult. In cold weather concreting, an accelerator can be added to speed up the setting time and strength development of the concrete. A water-reducing admixture can reduce the amount of water required to produce concrete of a given consistency or to increase the slump of the concrete. Pozzolanic materials such as fly ash can help reduce internal temperatures in concrete. High-range water reducers, commonly called superplasticizers, are additives that make normal concrete so workable that little or no vibration during placing is required. Superplasticizers can also be used to produce concrete at much lower than normal water-cement ratios. These concretes with a silica fume admixture can achieve very high strengths, many with compressive strengths in the 10,000 to 15,000 pounds per square inch range. Although effective when used properly, all of these admixtures complicate the quality control process. Only materials conforming to their relevant ASTM specifications should be used, and then only after laboratory tests have confirmed that they will produce the desired properties in the concrete. These basic ingredients of concrete, cement, water, air, coarse and fine aggregates, and admixtures where necessary, combine into a homogeneous mass during the mixing process. Freshly mixed concrete should be plastic or semi-fluid, capable of being molded by hand, and workable when placed and finished. Workability is the term used to describe the ease with which concrete can be placed and consolidated without bleeding and segregation. Concrete made with too much water will flow easily, but the coarse aggregates tend to separate from the paste and settle to the bottom, a condition called segregation. A mix as sloppy as this will result in poor, non-uniform concrete, and it will not be workable. Bleeding occurs when water rises to the surface as the solid particles in the mix settle toward the bottom. To minimize segregation and bleeding, use the stiffest practical mix of concrete. Finishability refers to the ease with which the surface of the concrete can be worked with finishing tools. Stiffer mixes with low water-to-cement ratios can be placed without difficulty if the concrete is consolidated by either hand rodding or vibrators. Consolidation compacts the concrete into the forms and around reinforcement and eliminates air pockets. Mechanical vibrators loosen up stiff mixes, making them more fluid and workable without adding water. They make it possible to economically place quality concrete that would be impractical to place by hand. From the time the ingredients are first mixed together, the mixture begins to harden. The cement and water in the paste react chemically in a process called hydration. New chemical compounds are formed from the union of cement and water that bind all of the elements in the mix together. These new compounds give concrete its engineering properties: strength, durability, water tightness, stability, and resistance to abrasion. Hydration continues as long as moisture is present and temperatures are favorable. That is why properly made concrete, unlike other materials, grows stronger as it grows older. As the cement hydrates, it releases heat. In wintertime, this helps protect the concrete against damage from freezing temperatures, but may cause internal stresses in massive structures such as dams. Different types of cement release heat at different rates. The approximate amount of heat generated during the first 7 days based on 100% for Type 1 Portland cement are Type 2, 80 to 85%, Type 3 up to 150%, Type 4, 40 to 60%, and Type 5, 60 to 75%. The rate of hydration determines the setting and hardening time of the concrete mixture. Gypsum added to the cement regulates the initial rate of hydration, although other factors can influence this rate as well. As we have noted, concrete needs moisture to hydrate, harden, and gain strength. When concrete dries, it stops gaining strength. This chart shows how curing time affects strength gain. Air-entrained concrete made with a water-cement ratio of 0.5, 1/2 pound of water to 1 pound of Portland cement, will typically show a strength of about 2,000 pounds per square inch after 7 days curing. The 28-day strength will be around 3,500 pounds per square inch, and at 6 months will be 4,500 pounds per square inch if the concrete is continuously moist cured. If curing is stopped and the concrete allowed to dry, there is very little further strength gain. Concrete test specimens cured only 7 days level off at about 3,400 pounds per square inch. Concrete cured only 3 days reaches a maximum strength of only 2,800 pounds per square inch. Concrete that is not cured at all gains only slightly more than 1/2 of its potential strength. As long as concrete is kept moist, it will continue to grow stronger. Wherever concrete is subjected to hydrostatic pressure, as in pipes, dams, seawalls, or to severe weather conditions, it must be watertight. Watertight concrete is achieved with low water-to-cement ratios, air entrainment, and extended curing time. This is demonstrated in the laboratory with this special apparatus. A hardened concrete cylinder of known water-cement ratio is inserted into the chamber and subjected to water under pressure for a specified time. Leakage through the cylinder is collected and measured. Cylinders with a low water-to-cement ratio were watertight after only 7 days of curing. Cylinders with a high water-to-cement ratio still leaked after 14 days. Concrete for industrial floors and pavements should be highly resistant to the wear and abrasion they experience from heavy and continual traffic. Abrasion resistance can be measured in the laboratory by this machine. It subjects a concrete specimen to continuous wear from rotating discs or dressing wheels loaded to a constant weight. The surface of the specimen is measured using a micrometer and bridge before and after the test. The depth of the concrete worn away in a specified number of revolutions indicates the wear resistance of the concrete. Test results indicate that abrasion resistance is closely related to the hardness of the aggregate and the strength of the concrete. Once again, concrete with a low water-cement ratio and adequate curing should be used to provide the strength needed to resist abrasion. Concrete that is normally used in pavements, buildings, and other structures has a unit weight in the range of 140 to 150 pounds per cubic foot. The unit weight or density of concrete depends primarily on the type of aggregates used, the amount of air in the mix, and the water and cement content. For special uses such as roofs, firewalls, and floor fills, lightweight insulating concretes can be produced with unit weights as low as 15 pounds per cubic foot. This ultra-low weight results from the use of lightweight aggregates such as perlite, vermiculite, or expanded polystyrene beads. Structural lightweight concrete ranges in density from 90 to 115 pounds per cubic foot. It is made from lightweight aggregates such as expanded shale, clay, slate, and slag, or sintered fly ash pellets. Heavy concretes produced with special heavyweight aggregates have unit weights as much as 400 pounds per cubic foot. They are used primarily for radiation shielding, but also for counterweights and other uses where high density is important. Hardened concrete expands or contracts slightly due to changes in temperature, moisture content, or sustained stress. These volume changes are minuscule, but are the source of cracks that occur in hardened concrete. When concrete dries, it shrinks. This will cause random cracking unless joints are placed at intervals to confine shrinkage cracking to these controlled locations. Control joints are grooved, scored, or sawed in sidewalks, driveways, pavements, and floors so that any cracking will occur at these joints. Architectural concrete walls are jointed for the same reason. Isolation joints separate a slab from other parts of a structure so that the slab can expand and contract without the restraint that can cause cracking. Isolation joints extend the full depth of the slab and include a pre-molded joint filler. Construction joints are placed when concreting work is done for the day. They separate areas of concrete placed at different times. This has been an introduction to the fundamentals of quality concrete, what it is made of, how it is made, and how to attain the desirable properties in fresh and hardened concrete. Quality concrete takes a concentrated teamwork effort by the project engineer, the concrete producer, the concrete contractor, and the inspection and testing agency involved in the project. Quality concrete is made of clean water, Portland cement, and well-graded aggregate. These common materials can also produce poor concrete. The difference in quality depends upon how well you understand and apply the fundamentals discussed in this presentation to the 5 essential requirements of quality concrete. Proper selection of materials, correct proportioning and mixing and transporting, careful placing and consolidation, skillful finishing, and adequate curing. It is the careful attention that you pay to these simple basic principles that produces quality concrete every time.